Okay, you know, I thought I'd spice it up a little bit here. There are four phases of matter, right? There's solid, and solids are where the molecules are relatively fixed with respect to each other, right? Some solids are crystalline. Some things like metals are just sort of the electron clouds sort of overlap, and that's why you can reshape metals with a hammer because you can they're sort of metallic, right, or something like that. They're malleable. That's the word. There's liquids, right, and liquids are like greased marbles, right? If you can sort of imagine, they all sort of stick together and they can slide around each other. A gas is a bit like ping pong balls in a room full of fans, right? They're just little particles whizzing around. Now remember that a gas is mostly nothing. So the space between a gas is there's nothing there. It's not like gas is going through something, right? Which is sort of interesting, right? And then if you heat it up even more, every collision, if the particles have enough kinetic energy, every collision rips the electrons off, right? So the electrons, basically plasma is just a sea of nuclei and electrons. And so, of course, the outstanding thing about plasmas is that plasmas conduct electricity really, really well. Even something like helium, which never gives up its electrons, is you have to give up your electrons. Your plasma, right? So this is a picture. This is a crystalline solid here. This is a lattice. This would be like sodium chloride. I think makes little cubic crystals like that, right? This is supposed to be a liquid, right? Only there's too big a gap here, right? This would be a somewhat compressible liquid, right? These guys are all just sort of sliding by each other like that, but they always stay touching each other, and that's why this has about the same density as this. This is not as big a change. These latent heats are always smaller because that's a smaller change. But of course, this is gas is just like those particles. You saw the little overhead transparency. These guys are just bouncing around. The collisions that they make with the containers and with each other are purely elastic. And whoops, that he's spinning. Why did I draw it like that? Okay, so those are our phases, right? And then I think you're familiar with this graph, right? This is for water, right? Water has a concept zero. This is its melting point or freezing point, right? I always like to think, cup half full, right? And then this is the Berlin point, right? So assuming that you're at one, let's see if I can do this. Assuming you're at, boy, look how good I am at drawing straight lines. I did not hold the shift key down. Okay. Okay, what was I saying? I was so impressed by my straight line, right? This is the boiling point, right? So first off, that boiling points and melting points, those are temperatures, okay? And then in this region here, of course, we are changing the kinetic energy, right? That would be an MCAT type of thing, right? And then in here, we're changing the potential energy. So that's going to be an ML calculation, right? Then we are in this region also now anytime the temperature changes, right, the kinetic energy is changing. So remember that temperature is proportional to kinetic energy. And so this formula is the kinetic energy formula because it's got temperature in it. That's your kinetic energy parameter, right? This is just a indicator. Oh, they're just loud up there. Okay, this is an indicator of the potential energy, right? Again, this is another potential energy thing here, right? Okay, and then this is another kinetic energy, right? So that's going to be an MCAT. So if you wanted to figure out all of this heat, you'd have to go MCAT plus ML plus MCAT plus ML plus MCAT, right? And I'll give you problems where we'll start with so much liquid here and go to steam here, and you've got to go MCAT plus ML plus MCAT. Okay. Notice this is a graphical ellipse, and the reason that they did this in this graphic is that this is 3.33 times 10 to the 5th. This is 22.6 times 10 to the 5th. So really it should be 6.8 times longer, but it's not really. It's like 4 times longer. So they did that. I think in the new version of the book, this is from the old version, they don't have that ellipse in there. But anyway, yeah. Okay, so let me just show you this. This is, we're going to look at the melting point and boiling point for this. Okay. And the first question is, what is the melting point? What's the boiling point? Well, you just got to read the graph here. It's where the plateaus are. This is melt. This is boil. Okay. So melting here is happening between 20 and 30. Okay, so I think it's what, 25 degrees? Is that right? 25. Okay, and then boiling is happening between 70 and 80, so I think it's happening at 75 degrees. Yeah? Okay, so those are our melting and boiling points. And those are temperatures. So let's look at the next thing, right? The next thing says, what is the specific heat of the solid phase? Well, here is our solid phase right there. That little guy there, right? And the specific heat is going to be, if Q is MCAT, right, then C is equal to, well, it's got to be Q over M delta T, right? Q divided by M delta T, right? And so we've got the mass right there. It's 0.45 kilograms, right? That's graph reading, isn't it? Okay, and then let's see. The Q that flows in is, this is heat here, right? Okay. So this is in 1,000 joules, right? So this is 5,000 joules, I think, right? This is 10,000, 20,000 joules. So the heat that flowed into just the solid phase is 5,000 joules, right? So C is equal to 5,000 joules divided by C divided by M delta T, right? So M is 0.45. And then delta T is from 0 to 25, right? So that's 25. Okay, so I can do this. 5,000 divided by 0.45 divided by 25. And I get 444.444, right? Right, repeating, this is joules per kilogram degrees Celsius. Right? That's our units. This is degrees Celsius, right? Joules per kilogram degrees Celsius. So you can read these graphs and actually determine this stuff from it. And I'm just going to keep going through and showing you how to find this, and then this, and then this, and then this. And I'm pretty sure at some point you'll figure it out for yourself and stop watching this video. Okay, so the specific heat of the liquid phase is this guy here, right? There's where it's liquid, right? This is solid, liquid, gas. This is liquid plus gas. This is solid plus liquid, right? Okay, so for the liquid phase, Q is MCAT. So therefore C is Q over M delta T, right? Right, so that's going to equal, the heat that flows in is, well, it starts there and it ends there. So what is this? This is 35,000 minus 15,000. Is that 10, 20,000? Yes, it is. Right, so the trick here is you only want to look at what flowed into the liquid, right? And so if you do the liquid here, right, and you draw a nice straight line down like that, right? Okay, this distance right here is from 15,000 to 35. That's 20,000 joules, right? And that's all that flowed into the liquid. Okay, and then the mass is 0.45, right? And that's just written up here, right? And then delta T for this guy is from 25 to 75. 25 to 75 is 50, right? Okay, so 20,000 divided by 0.45 divided by 50. And this is 888.888888888. Okay. Now remember, this one was 444, right? So the bigger the number, the lower the slope. Is that right? I guess that makes sense, right? Because it's harder to heat up, right? Okay. So what's the specific heat of the gaseous phase? You said gaseous phase. Okay. Well, the heat that flowed in, we know by this point that C is, what is it? Q over M delta T, right? Okay. So the Q that flowed in is from 60 to 70, right? Okay. So that's 10,000 joules, right? And then the mass is still 0.45, right? Kilograms, and then the delta T is from what? This is 75 to 90. Is that 15 degrees, right? So 10,000 divided by 0.45 divided by 15. 14, 1, 4. Oh, this is cool. This is a cool number. 8, 1 point. I collect repeating numbers. It's 481, 481, 481, 481, 481. Right? That's crazy. I love that. Next number is a 4. Anyway, this is joules per kilogram degrees Celsius. Okay. So that's that, right? Okay, so now let's do a latent heat, right? Fusion is this guy. This is fusion. This is vaporisation, as the Brits would write. Did I spell that right? It looks right. Okay. This is even easier. Q is ml, right? So L is going to be Q over M, right? And the heat that flows in for fusing it, apparently, right? Here, I got to do I love my straight line. I'm just very excited about that. Look at it. That other line was pretty good without wow. I drew that by freehand, or maybe I didn't. Okay, so I don't even know. Okay, 10,000. Sorry, 10,000. It's supposed to be a comma, right? From 5,000 to 15,000, right? Is our Q, and then our M is 0.45. I think this is 10 divided by 0.45. I think it's 22. It's 22, 2, 2, 2. I think things like with 0.45 like that make a lot of repeating numbers. This is joules per kilogram, right? There's a lot of 2's. There's way more 2's than that. I'm not even writing half of them down here. Okay. And then latent heat of vaporisation. Well, that's here, right? That's this guy. Vap. Okay, so Q is ml. So L is Q over M. So that is how much heat flows in. Let's do it here. So we don't even need a line. We already got a line. I wanted to draw a line. 10,000, 20,000, 25,000, right? Right, divided by 0.45 kilograms, right? So 25,000 divided by 0.45. That can't be repeating. Indeed it is. It's 55,555.55555555555555556. Anyway, this is joules per kilogram. Yay.